problem 26 wants to know the slope of the tangent line to the polar curve, r equaling 1 plus 2 sine theta at theta equaling 0. So the slope of the tangent line, when they ask it like that, they basically mean like if you're to graph this and then superimpose an xy plane, what's the slope of the tangent line? So they're asking you for dy dx, good old-fashioned dy dx, when theta equals 0. That's what they want. And then, you might think, well, how on earth would I get this, So we have the, the idea of defining a derivative in terms of a parameter. And so dy dx could be thought of as dy d theta divided by dx d theta. So then all we'd have to do is get dy d theta and dx d theta separately, and then we can just kind of put these in like little building blocks. So so how are we going to do that, right? Well, so dy d theta means dd theta of y. So we need to get y in terms of theta. So what is y in polar form? What's the conversion? So the answer would be it's equal to r sine theta. And if that seems like complete voodoo, just a quick reminder, if you have a right triangle, let's say it was graphed on an xy plane, if this is the point xy, and this is theta, and this is r, then this would be x, this would be y, and so sine of theta would be opposite over hypotenuse, so sine of theta would be y over r, and then you can multiply both sides by r, and then you have this. So hopefully this doesn't seem like something totally made up. Anyway, so we have that. Erase this off. Probably need that space in a second. And then we need this to be totally in terms of theta so that r is a problem. But that's where this definition for this problem, they defined r in terms of theta right there. So you're just going to make that substitution. So for this problem, y is 1 plus 2 sine theta, and then bring down that sine theta there. Okay? All right, up to you how you want to go about this. I personally would distribute sine theta in. And then take dd theta both sides. Like so. You could leave it like this, or you could use a double angle formula for sine swap to condense this down just a little bit. Totally up to you. So that's dy d theta. So now we know what we can put in up here. And then dx d theta, you do the same thing, but x is defined as r times cosine theta, making the substitution for r using their definition up here. You'd have 1 plus 2 sine theta times cosine theta, and then distribute it in, like so. And then before I take the derivative, I love avoiding product rule personally. It's not like I can't do it, it's just more of I don't want to. So I prefer to replace that. So I'm not doing the derivative at all. I'm just replacing that with sine of 2 theta. You do not have to do that, but it's kind of nice. So then dx d theta would end up being derivative of cosine is the opposite of sine. Derivative of sine 2 theta would be 2 times cosine 2 theta, which if you could use product rule on this, you'd end up with something that is just this, but expanded out. Okay, so now let's figure out, well, what would dy d theta be at this moment when theta is 0? So cosine of 0 is 1. Plus 4, sine of 0 is 0, and cosine of 0 is kind of who cares because you're going to multiply it by 0 anyway. But anyway, so we ended up with 1 there. Dx d theta, when theta is 0, would be negative sine of 0 is 0 plus 2 times cosine of 2 times 0, which is just 0. Cosine of 0 is 1. And so we'd end up with, like I got +1 again. Interesting. Okay. Says what's the slope of the tangent line? And so we basically would just come up here. So dy dx at the moment when theta is 0 would end up being, it looks like 1/1. Which, darn it. Oh no, that's a 2. Woo! 2 times 1 is 2. Aha, right here. 2 times 1 is 2. You probably noticed that. Anyway, so that's a 2. Okay. Now, is there an option that matches with what I got? Yeah, good. Perfect. So hopefully the answer, option B, hopefully the answer is B for that one.